Okay, have you ever thought about what happens when you mix something really precise, like differential geometry, curves, surfaces, with something inherently messy, like probability? It sounds a bit like mixing oil and water, maybe,
Hmm.
but the result is this fascinating field called information geometry.
Exactly. It's quite a powerful blend.
So today we're doing a deep dive into information geometry and these things called statistical manifolds. Our mission really is just to get the core ideas across quickly. It's specialized stuff, but super interesting.
Hmm. At its heart, information geometry applies the tools of differential geometry to probability and statistics. We study statistical manifolds. Think of it like this. Each point on this special kind of surface, or manifold, represents an entire probability distribution.
So like one point could be one specific bell curve, another point a slightly different one.
Precisely. And the space they all live in has geometric structure. It's a Riemannian manifold.
Okay, geometry for probability. And I read something quite specific, almost surprising,
Hmm.
that the set of all normal distributions, all those bell curves,
Ah, yes. That set forms a statistical manifold that actually has hyperbolic geometry, like Escher's drawings.
wow, so not flat Euclidean space at all. It's intrinsically curved.
Absolutely. That's a key takeaway. Standard Euclidean distance just doesn't accurately capture the distance or difference between probability distributions, especially when parameters have constraints, like variance needing to be positive. The geometry arises naturally.
That really drives home why we need this different approach. Okay, fascinating. And before we map out more of this landscape, just a quick word about our sponsor. This deep dive is brought to you by embersilk.com. Embersilk is the answer for all your AI education and integration needs, so check them out, embersilk.com. All right, let's dig into the foundations. This isn't a totally new idea, right? Where did it start?
No, not brand new. The roots go back surprisingly far. C.R. Rao, back in 1945, they was the first to really see the potential of treating the Fisher matrix, a concept from statistics,
Yeah.
as what mathematicians call a Riemannian metric, a way to measure distance on a curved space.
1945, wow. But the modern theater?
The modern, more systematic development, a lot of that is thanks to Shunichi Amari. His work really shaped the field as we know it today.
And the central tool is this Fisher thing, the Fisher information metric.
Yes, the Fisher information metric. It's really the natural choice for measuring distance on these statistical manifolds. What it does, essentially, is quantify how distinguishable two nearby probability distributions are. If you tweak the parameters just a tiny bit, how much does the probability distribution change? The metric captures that sensitivity.
So it's like a perfectly calibrated ruler, but specifically designed for measuring changes in probability models on this curved surface.
That's a good way to put it, yes.
Okay, so the space is curved. We have this special metric.
Hmm.
What's the payoff? Where does this geometric view actually, make a difference in the real world?
Oh, the applications are quite broad. Anywhere you're dealing with families of models and trying to find the best fit or understand relationships, think statistical inference, time series analysis, even quantum systems.
And critically, machine learning, right? I keep hearing about that connection.
Absolutely critical there, especially in optimization. How do you find the best parameters for a complex model? You see, for certain families of distributions, like the exponential family, the geometric structure is very rich. You don't just get the Fisher metric. You also get things like two complementary flat ways to define connections, think ways to define straight lines, and something called a canonical Bregman divergence, another distance measure.
Okay, so multiple tools baked into the geometry itself. How does that help with, say, training a neural network?
Well, think about finding the minimum error. On a curved surface, the steepest downhill path isn't necessarily the shortest or most efficient path to the bottom.
Right, like walking straight on a globe doesn't follow the equator.
Exactly. Standard optimization methods often use Euclidean, straight-line assumptions. They take the steepest path in that flat sense. But information geometry lets us develop methods like natural gradient descent.
Ah, I've heard of that one.
It doesn't follow the simple gradient. It follows the true steepest path on the statistical manifold, using the Fisher metric. It follows the geodesic.
The statistically shortest path.
Yes. And this often leads to much faster and more stable convergence, especially for complex models like deep neural networks. You also see mirror descent, which is related. Beyond ML, there's biology, statistical mechanics, even mathematical finance finding uses for it.
So to wrap up this dive then, information geometry gives us a powerful new perspective. It turns the abstract world of probability distributions and statistical models into a tangible geometric landscape. We can measure distances, understand complexity, and find optimal paths using these geometric tools, like the Fisher metric.
It provides a rigorous language for uncertainty. And maybe a final thought for you to consider. We know modern AI, especially neural networks, are leveraging these geometric ideas for efficiency. So what fundamentally new insights about learning itself, about how systems generalize from data, might we unlock by continuing to explore this idea of probability distributions living on curved spaces? What does the shape of that space tell us about intelligence?
A deep question indeed. Something to ponder. Thank you for joining us on this deep dive.